When commentators say a missile can't be jammed, they rarely mean absolute immunity. Instead, the phrase captures a relative resilience, a missile whose guidance and targeting systems make it much harder, slower, or more costly for defenders to degrade its accuracy with electronic attack. Modern air defenses rely heavily on degrading an attacker's sensors or the data links that guide weapons. Resilient missiles instead use layered guidance, autonomy, and sensor fusion so that loss of one input doesn't doom the weapon. For Iran, developing such resilience is about operational effectiveness under contested electromagnetic environments, not magical invulnerability. In practical terms, resilience means the missile retains acceptable accuracy enough to threaten high-value assets even when defenders deploy jamming, spoofing, or cyber measures. That resilience is achieved through a mix of redundancy, multiple ways to navigate and aim, passive sensors that detect the environment without radiating, relative navigation techniques that depend less on external signals, and terminal guidance that relies on onboard sensors that are difficult to blind remotely. Importantly, these characteristics are part technological and part doctrinal. Resilience also depends on tactics, timing, and the platform's mission profile. For a small state facing sophisticated adversary air defenses, investing in weapons that remain useful in jammed environments is an asymmetric way to raise the cost of confrontation. Iran's missile development traces back to the Iran-Iraq War in the 1980s, when ballistic and cruise missiles emerged as tools of strategic deterrence and regional power projection. Over decades, Iran pursued both reverse engineering and indigenous improvement, acquiring foreign hardware, learning from proliferation networks, and building domestic capability in propulsion, guidance, and command systems. A persistent driver has been geography and deterrence. Iran sits in a neighborhood where access to friendly basing is limited, and theater-range missiles offer a practical way to hold distant targets at risk. Early programs focused on ballistic missiles for strategic deterrence. Later efforts expanded into cruise missiles and anti-ship variants tailored to regional choke points like the Strait of Hormuz. As adversaries improved electronic warfare (EW) and integrated air defenses, Iranian developers adapted, shifting design emphasis toward survivability in contested electromagnetic environments. That historical continuity explains why later systems place greater premium on autonomy, sensor fusion, and robustness. Iran's strategic calculus emphasizes weapons that still function when network support is degraded or when satellites and data links are contested. Technical choices follow doctrine. Iran's military and paramilitary forces have prioritized asymmetric options that can threaten larger adversaries without matching them platform for platform. The emphasis is on distributed launch, standoff range, low cost relative to Western systems, and the ability to operate under electronic attack. That doctrine encourages designs that are simple to produce yet hard for defenders to neutralize. See skimming cruise missiles with low radar cross-section, ballistic missiles with unpredictable terminal maneuvers, and glide vehicles that complicate radar tracking. Operational concepts, saturation attacks, salvo launches from dispersed platforms, and mixed profiles combining ballistic and cruise weapons, are intended to overload layered air defenses and exploit any vulnerabilities. Politically, the desire to deter embargoes, convoy interdiction, or strikes on maritime commerce also shapes priorities. A missile that reliably reaches a ship or base even while its guidance is partially degraded is strategically valuable. Thus Iran's anti-jamming advances are partly a response to the specific mission tasks its forces expect to perform in the Persian Gulf, Levant, and Eastern Mediterranean theaters. The central way to resist jamming is by not relying on a single navigation or guidance source. Western precision weapons often depend heavily on GPS or equivalent satellite navigation, a dependency that can be exploited by defenders. Systems that are resilient instead combine multiple navigation methods, inertial navigation systems, INS, that use onboard accelerometers and gyroscopes, terrestrial-based navigation aids, terrain matching where possible, and celestial or visual cues. Crucially, these are fused. If GNSS, Global Navigation Satellite System, signals are lost, the INS temporarily carries the weapon. If INS drift grows, terminal sensors like radar seekers, imaging infrared, IAR, or electro-optical, EO, cameras correct the aim. Iran's approach, as publicly discussed by analysts, favors sensor fusion and graceful degradation. the missile keeps hunting with available data, rather than failing catastrophically when one sensor is jammed. This architectural choice, redundant, layered guidance, raises the technical bar for jammers. An effective block would need to disrupt multiple, different systems simultaneously, which is harder and more resource-intensive. One straightforward way to make a weapon harder to jam is to reduce what it transmits. Active sensors and data links broadcast emissions that adversaries can detect and target with EW. Passive sensors, passive radar reception, imaging seekers, listen to the environment or rely on reflected ambient energy rather than emitting their own signals. A passive seeker cannot be jammed in the classic way because it doesn't present a signal to jam. Instead, defenders must deny the environmental cues or employ decoys. For ship targeting, passive electro-optical or infrared seekers lock onto thermal or visual signatures. For land targets, terrain features and optical landmarks can be used in the terminal phase. Iran's investments in seekers, multispectral imagers, and algorithms that can match observed scenes to stored references are elements of this strategy. Passive sensing reduces electronic footprint and complicates defenders' task, though it also places demands on processing power and image libraries, and performance can fall in degraded visibility, fog, smoke, night, and less complemented by other sensors. Another non-technical but highly effective approach is mission design, altering flight paths, speeds, and altitudes to minimize exposure to the most dangerous EW coverage. Low-altitude, sea-skimming flight reduces radar detection time and forces radars to contend with sea clutter. Terminal maneuvers, randomized or pre-programmed evasive actions, complicate tracking solutions and can defeat simple predictor-based jamming strategies. Additionally, variable timing and dispersed launch platforms shorten the warning window for defenders. Iran's doctrine includes salvo launches from small craft, coastal batteries, and aircraft, producing multiple, simultaneous threats that dilute the defender's ability to concentrate jamming on a single missile. While maneuverability doesn't make a missile unjammable, it reduces the defender's margin to launch effective EW at the most critical guidance phases, especially when combined with redundancy in sensors. Because satellite navigation can be jammed or spoofed, resilient systems adopt alternatives. Dead reckoning via inertial systems, terrain contour matching, TERCM, and visual odometry are all used to maintain position without external signals. Another high-value approach is relative navigation. The weapon references a moving or fixed platform, a mother ship, an airborne relay, or even distinctive terrain features, rather than absolute coordinates. Relative systems make it harder for defenders to mislead the missile by attacking GNSS signals, because the weapon homes to a sense target signature or a moving beacon that may itself be harder to detect. Iran's development of coastal defense missiles and anti-ship weapons benefits from relative approaches. A missile that homes to a ship's radar/infrared signature or a maritime beacon will be less affected by GPS outages. These schemes require reliable local sensing and signal processing, but they shift the defender's burden from jamming a satellite signal to masking platform signatures or physically intercepting the weapon. Even if a missile's mid-course guidance can be disrupted, the terminal phase, the last seconds before impact, often determines mission success. Investing in robust terminal seekers, imaging infrared, millimeter wave radar, optical correlation, allows a weapon to reacquire and home on a target despite prior guidance errors. Terminal seekers typically have limited exposure to EW, operate at higher frequencies or in spectrum bands where defenders have less coverage, and can use onboard processing to discriminate decoys. Iran's more advanced missiles and cruise variants emphasize terminal autonomy, a strike vehicle that can autonomously identify a ship's signature or landmark and correct its trajectory in the last moments becomes far less vulnerable to mid-course jamming. That capability converts a degraded mid-course solution into an acceptably precise final impact, which is often sufficient for area targets or ships when weapons use data links for in-flight updates. Making those links resilient is crucial. Techniques include extremely short, bursty transmissions timed to reduce detectability, frequency hopping over broadbands, low probability of intercept/low probability of detection, LPI/LPD, waveforms, and using relay platforms, UAVs, aircraft, that limit link distance. Iran's publicly observed tactics, using regional airborne relays or shore-based networks, reduce exposure of critical links to long-range EW systems. However, these measures are not foolproof. A sophisticated defender with persistent surveillance can still locate and attempt to jam or attack relays. Thus, many resilient architectures combine short-range, hard-to-detect links with autonomy so that the weapon can operate acceptably for the remainder of flight. If the link is lost, physical stealth plays a role. Reducing radar cross-section, RCS, infrared signature, and acoustic cues makes detection and targeting harder, which indirectly improves survivability against jamming because defenders must first detect and track the weapon to jam it effectively. Iran has invested in shaping, materials, and flight profiles that reduce detectability, especially for cruise missiles and sea-skimming variants. The effect is twofold: shorter detection windows and lower signal-to-noise ratios for jammers attempting to find and target the missile's emissions or reflector. However, stealth is relative and depends on sensor sophistication. Low RCS can be offset by multi-sensor detection networks, radar plus infrared plus passive acoustic. Nonetheless, signature management is a cost-effective way to increase the difficulty of defending against a missile in an EW-rich environment. Iranian advances have been driven in part by necessity. Sanctions constrained access to high-end Western components, pushing Iranian engineers toward domestic production, modified commercial off-the-shelf, COTS, electronics, and creative supply chains. That context incentivized modular, reparable systems that can be upgraded incrementally and fielded at scale. Using COTS components cleverly, paired with robust software and mechanical design, lets developers implement features like sensor fusion and advanced signal processing without relying on embargoed chips. At the same time, indigenous production fosters security of supply. Components can be produced locally and modified to resist tampering or cyber intrusions. The downside is that constrained access can limit the highest-end performance, but for many mission sets, regional strike, anti-ship, or anti-access denial, a resilient architecture built from available parts can be operationally effective. Resilience also comes from testing and operational experience. Iran has conducted many live launches, exercises, and maritime drills, each serving as a testbed for software updates, seeker tuning, and tactics. Iterative testing, even if lower in sophistication than Western programs, allows rapid feedback loops. Developers see how seekers perform against clutter, how navigation drifts over long flights, and how different flight profiles interact with local weather and geography. This iterative learning is especially valuable when adversaries adapt. Developers can field software patches and revise tactics to counter new defensive measures. The pattern of incremental improvement, not a single breakthrough, explains how gradual investments yield systems that are increasingly hard for defenders to neutralize with off-the-shelf EW. The missile that can't be jammed in isolation is less impressive than one integrated into a wider attack package. Iran often plans combined use of drones, electronic attack assets, decoys, and conventional missiles in coordinated salvos. Drones can act as decoys or jammers themselves, drawing defensive attention and degrading sensor performance before the main strike arrives. Simultaneous ballistic and cruise launches create multiple threat types that stress different parts of a defense network. This integration complicates EW. While a defender may jam a particular frequency or spoof a satellite signal, the combined package may include passive seekers and terminal autonomy that circumvent that single mitigation. In short, resilience is amplified by synergy. Combining persistent ISR, autonomous terminal guidance, and multi-vector attacks reduces the effectiveness of single-point countermeasures. Every improvement creates a response. As Iran fields more resilient seekers and guidance methods, potential adversaries adapt with multi-layered detection, multi-static radar, infrared tracking, directed energy defenses, and networked sensors that cross-cue one another. The result is an arms race dynamic. More sophisticated passive seekers spur development of advanced decoys and signature management tactics. Resilient data links prompt investment in hunting relays and kinetic strikes on launch nodes. Thus, describing a missile as unjammable captures a moment in this dynamic interplay, not a permanent condition. For policymakers and military planners, the key insight is that investment in adversary resilience must be met with investment in integrated detection and layered defense, and that no single technological silver bullet will permanently solve the contest. Iran's development of resilient missiles has political and legal ramifications. Neighboring states and global powers view improved strike capability as a force multiplier that alters deterrence calculus, prompts regional arms buildups, and raises risks of escalation. There are normative questions too. The easier it is for a state to threaten commercial shipping or foreign bases, the more likely naval convoys and insurance costs rise, and the more incentives there are for preemptive countermeasures. International law constrains some behaviors but does not eliminate strategic competition in missile tech. Ethically, analysts worry about proliferation. Techniques that increase resilience can be exported, spreading capabilities that complicate global arms control. Hence, the phenomenon isn't purely technical, it reshapes regional security dynamics and international diplomacy. A relevant concern is the transfer of resilient missile concepts to proxies or other states. Iran has exported missile components, know-how, and whole systems to allied actors in the region over time, even if direct transfers of advanced seekers are limited, doctrinal lessons and low-cost design approaches can spread. Proxy forces with limited technical expertise can still leverage tactics, salvo launches, decentralized command, and passive seekers built from commercial parts, to make their attacks harder to defeat. Proliferation increases instability because it lowers the technical barrier for asymmetric actors to threaten commercial or military assets, complicating defensive planning. For international security, addressing proliferation involves not just export controls but also maritime security cooperation and norm building around responsible weapon transfers. Defenders' response strategies emphasize integration and resilience too, networked sensors that fuse radar, infrared, and passive acoustic cues, persistent surveillance assets that deny attackers surprise, hardening of critical nodes, and layered interceptors that affect different threat phases. Importantly, defenses benefit from diversity. No single sensor or frequency band should be the sole source of targeting data. Policies that reduce single points of failure, redundant data links, protected communications, and distributed command, raise the cost for attackers trying to exploit EW. Investments in passive detection and cross-queuing are particularly effective against low-emission threats, while diplomatic and economic measures can constrain the production and deployment paths of problematic systems. Note, this paragraph remains deliberately high-level and does not provide tactical or technical instructions on defeating specific systems. Building resilience is not free. Adding redundant sensors, higher quality seekers, and sophisticated processing increases unit cost and requires logistics for maintenance and upgrades. Iran balances these costs against operational need. For strategic denial or anti-access missions, a somewhat more expensive missile that works under jamming conditions may offer better return on investment than a cheaper, easily disrupted weapon. The economics also affect proliferation, lower-cost resilience techniques, creative use of COTS sensors, software improvements, can be replicated by smaller actors, while the highest-end countermeasures remain expensive. For defense planners, understanding the cost-effectiveness of adversary options informs procurement and deployment choices. Sometimes quantity plus simple resilience is politically and operationally preferable to a smaller number of very advanced units. Open-source reporting and defense analysis indicate incremental improvements in Iranian seekers, software, and doctrine rather than single breakthroughs. Imagery of launches, reported tests, and reverse engineering assessments suggest that Iran has steadily improved its ability to fuse sensor inputs and operate under contested conditions. Analysts point to more sophisticated terminal seekers, wider use of autonomous flight controls, and greater emphasis on salvo tactics. However, open-source assessments also note limitations: constrained access to certain high-end electronics, less rigorous quality control compared with advanced militaries, and logistical challenges. The net effect is a credible, operationally meaningful improvement in resilience, enough to concern regional navies and force planners, but not a leap to invulnerability. The central lesson is nuanced. Iran's missiles are harder to jam than older generations due to layered guidance, passive sensors, terminal autonomy, and doctrinal adaptations, but they are not invincible. Resilience raises the cost and complexity of defense, shifts the tactical balance in certain scenarios, especially in constrained theaters like the Persian Gulf, and compels adversaries to invest in integrated, multi-sensor defenses. For strategists, the implication is that asymmetric attackers can achieve disproportionate leverage through smart design choices and clever operational concepts. For the international community, the development highlights the need for diplomacy, export controls, improved maritime cooperation, and investment in layered, integrated defenses that address the multi-domain nature of modern missile threats.